Hello class, and thank you for watching. This is parts 2 of topic 2.1, the change in arithmetic and geometric sequences. In today's lesson, we're going to express geometric sequences today found in mathematical and contextual scenarios as functions of whole numbers. Now, yesterday we talked about arithmetic sequences or arithmetic sequences, however you want to pronounce that. Today we're going to focus on geometric sequences. Now, a geometric sequence does not behave like a linear function. This one behaves like an exponential function. We haven't covered exponentials in this course just yet. We will. And we'll talk about in more details what an exponential function is. Now, very similar to the geometric sequences, they are not going to be continuous. Now, successive terms have what is called a common ratio instead of a common difference. What this means is that there's a constant proportional change. So the percent of increase / decrease is always going to be the same. Now, the two formulas that we have for the geometric sequence are the following. The first one is that g of n equals to g sub 0 times r to the n power. This formula is the specific value of the expression of the equation of the geometric sequence if we know what the initial value is. So as long as we know what the initial value is and can determine what the common ratio is, or if we're given the common ratio, this is the formula that we use. Now there's a more general formula which can use with any value. And that formula is this, that g of n equals to g sub k, which is the k term in the sequence, multiplied with r to the power of n minus k. And this one works if we do not know what the initial value is. So this is the more general one that works with any sequence. Even if we know what the original one is, the initial value, this one also works. So this is the general one, which, like I said, works with any situation. So let's look at an example, first of all, what a geometric sequence looks like, okay? So a geometric sequence, again, like I said, has a common ratio. So what that means is that the values that we see right here, notice that here we have a geometric sequence, g of n is equal to 6 and 1/2 over n. If you look on the graph on the right here, this is what the graph will look like. The first number in the sequence, g of 0, is equal to the value of 6. The second number in the sequence, g of 1, is 3. And then the next number in the sequence after that is 3 over 2. And then we have 3 over 4 and 3 over 8 and so on, okay? So this is g of 0. Let me make it into a table instead, okay? Let me make this into a table. We have our n values, and we have the corresponding g of n value. So g of 0 is 6. When n is 1, g of 1 is going to be 3. G sub 2, g of 2 is 3 over 2. When n is 3, that value there is 3 over 4. When n is 5, that value, 4, when n is 4, that point that we have right there, that's 3 out of 8. And then we have two other points, 5 and 6, where I'm not going to fit right there. But again, this is what the values are. Okay, now this point right here is the sequence itself, okay? These are the numbers that we have as the elements in our sequence. Our sequence starts at 6, then goes to 3, 3 over 2, 3 over 4, 3 over 8, and then again it just simply continues. Now look at the common ratio. So we can initially see again that this is g of 0, the initial value. To get the common ratio, all we have to do is just simply get any number in the sequence and divide it, because it's going to be a proportional growth or a proportional change, divided by its previous number. So if I get this number right here and I divide it by 3, so 3 over 2, and I divide it by 3, which is the same thing as multiplying by the reciprocal. So if I flip the 3 and write it as 1 over 3, okay, and I multiply these two quantities together, that's going to be 3 over 6, which reduces to 1/2. So this right here is our common ratio, 1 over 2. Okay, and that's how you determine that value. And again, you could do it with any number. So probably a bit easier had I done 3 and I divided by 6. That's easy to see that 3 divided by 6 equals to the ratio of 1/2. But I wanted to use the fraction just to remind you how to divide a fraction with a whole number. To divide by a whole number, simply get the reciprocal of that value and multiply it instead of dividing. So it's like, again, from middle school, keep, change, flip. And that's how you divide a fraction by a whole number, or two fractions together. You keep the first one, you change the sign from division to multiplication, and you flip the second number and get the reciprocal of that. Okay, so now that we know, again, how this is uniquely different from arithmetic sequences, one of the things that we're going to look in today is determining the difference between an arithmetic sequence and a geometric sequence. Now, an arithmetic sequence, again, has a common ratio. So the formula, again, would have to be where we're multiplying a value of a sub n. That's going to equal to some geometric sequence. We'll call it G. G sub n will equal to G sub k times my common ratio of R raised to the power of n minus k, which is exactly what's going on here. This right here is an example of a geometric sequence. To verify it, this simply means that there has to have a common ratio. So if I do the same thing and I make a table, and I'm just going to do a couple of points and look what the value of S of n is when n is equal to 0, 1, and we'll do to 2, 1, 0, 1, and 2. Let's see what the output value is going to be. So to figure out what the output value, I'm going to start by replacing the n with 0. And I'm going to use a calculator to do this. And, well, I'm not going to show the calculations, but I'm just using a calculator to express this, okay? So in my calculator, I'm typing in 4 parentheses 2. And I'm going to raise that to 2 and only the 2 to the 0 minus 1 power. 0 minus 1 is negative 1. So I'm going to raise it to the negative 1 power. And that gives me an output of 2. I'm not going to replace the n value with 1. So 1 minus 1, this right here is 0. So it's going to be 4 times 2 raised to the 0 power, which is positive 4. And now I'm going to replace the value of n with the last input value, 2. And since 2 minus 1 is 1, this would be 4 times 2 to the first power. And that equals to 8. So with these values, you can see that the common ratio is 2. That when I divide 8 by 4, okay, that's going to end up multiplying by 2. Sorry, I'm going the wrong way. My arrow should be going downwards, okay? I'm multiplying by 2 to get that value, and I'm multiplying by 2 to get that value. And to know what number I'm multiplying to get the next number in the sequence, I just simply get any value and divide it by its previous one. So 8 divided by 4 is 2. So I'm multiplying by 2 to get that number. And 4 divided by 2 is 2. So 2 times 2 and 4 times 2 gives me those values. So since this has a common ratio, then this is an example of a geometric sequence. Okay. Now you'll notice again the format for this, well, you can recognize the format automatically that this is going to be an arithmetic sequence. But let's just review again. A sub n is equal to a sub 0 plus d times n. But just to review again, what's the difference between a geometric and arithmetic sequence is that an arithmetic sequence, that instead of having a common ratio, there should be a common difference. So we should be adding a positive or negative number to get to the next number in the sequence. So let's figure out what the numbers in the sequence are. Well, the first number in the sequence is obviously going to be 3, okay? Because if I replace this with 0, 4 times 0 is 0, and 3 plus 0 is going to be 3. Just that number right there. Now let's figure out what the second number in the sequence is. So S sub 1. So I'm going to replace this value with 1. And that's going to give us a total of 7. 4 times 1 is 4, plus 3, that's 7. And now I'm going to replace the value of n with 2. So 4 times 2 is 8, plus 3, and that's equal to a total of 11. Now notice that this is not a common ratio. Now we're not dividing the same number. 7 divided by 3 will say we're multiplying by 7 over 3, but 11 divided by 7 is 11 over 7. See, so there is not a common ratio. But if I subtract, I can see that to get from 7 and 3, I am adding 4. 7 minus 3 is the difference of positive 4. 11 minus 7 is a difference of positive 4. So I'm adding 4 each time. And if I continue the sequence, I would see again that that's the common, that this is the common difference. So this is going to be an arithmetic sequence. So this again is the type of sequence that this is. Now to distinguish between these values, well, again, if it's an arithmetic sequence or geometric sequence, then there has to be either a common difference or a common ratio. Well, using our intuitiveness, again, there's no way that this is going to be a common difference, because we're going from a positive number to a negative number, back to a positive, back to a negative. So that's no way that we're decreasing and then increasing and decreasing, because in order to be an arithmetic sequence, there has to be a common difference. So we would either only add a number to get the next value or only subtract. So this looks like it should be a geometric sequence. So let's see. If I get this value here and I divide it by its previous one, so negative 8 divided by 16, that equals to the fraction of 1 over 2. And if I get any other number, let's say 1, and I divide it by its previous one, 1 divided by negative 2, that is also equal to negative 1 over 2. And if I do 4 and 2, or negative 2 divided by 4, that also equals to negative 2. So since this has a common ratio, we'll again say that the common ratio is 1/2. We'll say r. Since the common ratio r is equal to 1/2, then this has to be an example of a geometric sequence. Well, here, this one, you'll notice again that the values of our numbers in our sequence are increasing, and they're increasing by 3. They go up by 3. 13 minus 10 is 3, 10 minus 7 is 3, 16 minus 13 is 3, and 19 minus 16 is a difference of positive 3. So since our common difference equals to 3, then this is going to be an example of an arithmetic or arithmetic sequence. Oh, I misspelled it over here. I just saw that right now. Okay, so this is an example in an arithmetic sequence, and this is an example of our geometric sequence. Okay, all right, now that we distinguish the difference between the two, let's look at some more examples of what skills we need to know for these type of sequences. Well, just like the previous examples, we need to know how to evaluate a geometric sequence. So let's begin with that. To evaluate a geometric sequence, well, let's fix my error here. There should be g of 0 and g of 4. We simply need to plug in, just like like any sequence, just simply plug in the corresponding subtext. So since g of n is equal to 4 times 2 to the n minus 1 power, g of 0 will simply replace the value of n with 0. And well, 0 minus 1 is negative 1. And if I just, I'm going to do this in the calculator. I'm going to just type this into the calculator. This would be 4 times 2 to the negative 1 power. Well, let me do it by hand. 2 to the negative 1 power is going to give me the reciprocal of that. Anytime I have a negative exponent, I have to flip the value and flip this number. So I'm going to get the reciprocal of this, and that changes the exponent from a negative number to a positive number. So this would be positive 1. So that means that g of 0 will equal to 4 times 1/2, only having one factor of 1/2 is 1/2, and 4 times 1/2, that equals 2, not 4, that equals to 2. So g of 0 equals 2. Now let's evaluate g of 4. Let me move this over to the side. Okay, so now let's evaluate the second one, g of 4. G of 4 simply is going to replace the n value with 4. Sorry, there should be a 1 right here. So 2, 4 minus 1, that gives us 3. So we're going to have 4 to the positive 3 power this time. Because it's positive 3, I don't have to get the reciprocal. I just need to multiply the number 2 with 2 3 times. So this is not 2 times 3. This is 2 times 2 times 2, which is a total of 8. So g of 4 equals to a total of 32. Okay, so now let's use one of the formulas to come up with a function for g, the sequence of g. So let's use an expression, and let's use that expression then to evaluate g of 4. Okay, now remember, there's two functions or two equations we can use. We can use g of n is equal to g of 0 times our common ratio raised to our n power. Okay, let me go back to the formula, right? Raised to the n power. That's one formula. The other option is the general one that works with any situation, which is my preferable one. This one right here. The only time that we can ever use this one right here that I'm going to highlight in yellow is if we know what the initial number in the sequence is. Okay, and in this example we don't know what that value is. We do not know what g of 0 is. We know what g of 1 is. So technically this would be the second number in the sequence. So we do know what the r is. We know that r is going to be 2. So what we're going to do is we're going to replace this number again right here. And let me highlight this. Okay. So here our g of k is going to equal to this value of 12. All right. So our k value is 1, and our g of k is equal to this value of 12. So the equation or the formula for g of n would be 12 times r, which we know is 2. And I'm going to use parentheses instead of my little dot right here. So 2. And I'm going to raise this to the n minus this k value, which in this situation is the value 1 because we're given the g of 1 value. So this would be the function for g of n. Now here we won't simplify. We're going to leave the expression as is. And this right here would be our solution. Okay, so this is the expression for g of n. So with g of n being this, I can now use this function to evaluate g of 4. So here is our expression. Here's the first part. And now for the second part. What is g of 4 going to equal to? Well, g of 4 would be 12 times 2 to the 4 minus 1 power. Now that we have g of n, we can now evaluate g of 11. So our function or our equation g of n equals to our g of k, which is 12, times our common ratio of 2 raised to the n minus 1 power. So that means that g of 4 would be 12 times 2 to the 3 minus 1 power. I'm sorry, 4 minus 1 power, which is 3. 4 minus 1, which is 3. So g of 4 equals to 12 times 2 to the 3rd power. And then just simply plugging this into the calculator. So 12 times 2 to the power of 3. That ends up going to equal to a value of 96. So there is your equation, or your value of G of 4. Now for the next problem right here, we don't have to use the general formula. G of n is equal to gk times r to the n minus k power. In this one, we could actually use the initial formula, G of n is equal to G of 0 times r to the n power, because we know what the first number in the sequence is. In this situation here, if I represent this again as a table, not x, I'm sorry, but n, the values of G of n when n is 0, according to the table is 9. I'm sorry, according to the graph is 9. Excuse me. When n is 1, the value of G, or the second number in the sequence, is 6. When G is 2, when n is 2, the third number in the sequence is 4. The other numbers are kind of hard to determine. As you see here, when n is equal to 3, we don't know what that y value is or what that output value is. The same thing with when n is 4, 5, 6, 7, 8, and so on. But with those, that's good enough to figure out what the common difference is. Since the numbers in the sequence are 9, 6, and 4, all I have to do is get any number and divide it by its predecessor to get the common ratio. Not difference, but the common ratio. So here, r will equal to 4 divided by 6, which reduces to 2 over 3. And since we know what the initial value is, again, G of 0 equals to this value of 9, that means that the function Gn is equal to the equation that starts off at 9 and is multiplied by 2 over 3 and raised to the n power. So to figure out the 13th term, G of 12, which is the 13th term in the sequence, I'm going to multiply 9 with 2 over 3 to the 12th power. And that is equal to the following decimal fraction: 4096 over 59049. And there is your value and answer for example number 4. Here's your function, your rule, and here is the value of G of 12, the 13th number in the sequence. Now let's look at example number 5. Now, if we're looking for the sequence, geometric sequence given 2 points, we're going to use both terms to create one equation in the general form. So remember, the general form of our geometric sequence is that G of n is equal to some G of k times our ratio raised to the n minus k power. And we're going to use the larger k value as the G of n value, or what we want to equal it to. From there, we're going to create an equation where we're going to solve for r using 2 steps, division and then a root, and then use either of the two values of r, use the value of r from step 2 along with either term given in the problem to write the general form of the geometric sequence. So let's look at example number 5. Here, to make a little bit more sense, I'm just going to put the numbers in their sequence in order. So we have G of 3 is equal to -2. So that means that the first value, we don't know what the first initial value of this sequence is, nor the second, nor the third, okay? So we don't know what the first 3 numbers in the sequence are, but we do know that the fourth number in the sequence, G of 3, which is the fourth number of the sequence, that's going to be -2. Then we don't know what the fifth number in the sequence equals, the sixth number in the sequence, sorry, that should be a G of 5, and G of 6, which is the seventh number in the sequence, that's equal to 128. So this is how we're going to create the equation using, again, this general form. We're going to start by using this number right here as the g of k value, okay? So the larger k value, or the larger value, is going to be the k value. That's going to be g of n here, okay? So we have two g of k's. G of k is 3, and g of k is 6. But we're going to use this one as g of n, okay? So like I said, look, this is how we're going to set up the equation. We start by looking at the first number in the sequence, or the prior number in the sequence, compared to its predecessor, right? So we're going to get this value here, -2, and that's going to be this quantity here. Let me highlight, color coordinate this. So this is going to be that number right there. So -2. We're going to multiply that with our value of r, which we do not know, and we're going to subtract the following values: the n and k value. The n value is going to be the larger of these numbers that we have here in the sequence. So the 7th term and the 4th term, okay? Those are the numbers we're going to subtract. Oops, I color coordinated them wrong. This one should be n, and this one is going to be k. And it should always be that the larger number gets subtracted by the smaller number. So it's going to be 6 minus 3 up there. And what we're going to set this equal to, we're going to set this equal to the further number in the sequence. So we start with the number that we know at the beginning, not necessarily the first number in the sequence, but the prior number in the sequence, and then we equal it to the number at the end of the sequence that we know. So in this case, we know the last number we know in the sequence is 128. So we set this equal to 128. And this is the equation that we're going to have. Now, to figure out the value of r, we're going to do the following two steps. The first step is to divide by -2. Again, this leading coefficient, since we're multiplying here, our r value is being multiplied by -2. We're going to do the inverse operation and divide by -2. So r is going to be raised to the 6 minus 1 power, which we can simplify now. We could do this in our head. 6 minus 3 is 3. And 128 divided by -2, that's equal to -64. Now, to get rid of this exponent of 3, we're going to take the third root to both sides. So I'm going to take the third root of r to the third power, and I'm going to take the third root of -64. And tomorrow I'll show you in class how to do that with the 84. So r to the third root of r to the third is simply going to be r, and the third root of -64 is -4. So there, now that I know what the value of r is, I can now come up with the general form of our geometric sequence. And I'm only going to substitute in again these three values. I'm only going to substitute in a value for g of k, for r, and for this k right there. Now the number that I use up here for g of k is the same corresponding number I need to use again for the k value right there. So there's two options. I can use 128 for g of k, and the equation will look like this. If I use 128, it would be 128 times r to the n minus 6 power. Okay, so that's one reasonable equation. That's an acceptable equation. Or if I use -2 instead of 128 for the g of k, -2, r would have to be raised to the n minus 3 power, which again is an acceptable value to use. So either one of these equations, okay, either this or this is the acceptable formula for g of n. And either one can be used to evaluate g of 11. So here, g of 11, let's use the first one first, would be 128. Oops, I forgot to do something. I should not be using just the letter r. I should be using the actual value for r, which we know is -4. So fix that. This should be -4. this number right there. So if I use the top one to figure out g of 11, this would be 128 times negative 4 to the 11 minus 6 power. Which again, just with the use of our handy dandy calculator, that's going to be 11 minus 6, that's 5, so negative 4 to the 5th power times 128. That ends up equaling to a total of negative 131,072. And if I use the second formula to figure out g of 11, so negative 2 times negative 4 to the 11 minus 3rd power, that is also going to end up equaling to, that also gives me a total of negative 131,072. Negative 2 to the negative 4th power. And since 11 minus 3 is 8, 11 minus 3 is 8, I will get negative 4, raise it to the 8th power, and then multiply that with negative 2, which, like I said, equals to the same value. Okay? So this is your answer for g of 11. So let's look at our sixth and final example. There are two corrections I need to fix. This one right here should be g of 2. The subscript should be 2. And this one should be 7, not 6. I forgot to change those because they should not match up to the previous one. So okay, so let's try this again. Let's look at this example now. So the strategy again is going to be the same. It's easy as we could recognize again what this means. G of 2 means that we're looking at the third number in the sequence. So we have g of 0, we have g of 1, and the third number in the sequence is going to be 48. We have g of, again, this is g of 2. We don't know what the fourth number, g of 3 is. G of 3, g of 4, g of 5, g of 6. But we do know that the eighth number in the sequence, g of 7, is going to be 1.5. Okay? So the way we're going to come up with the general form of our function is by starting right here. Okay? So we're going to start by writing 48 and multiplying 48 with our common difference r, common ratio r, and we're going to raise r to the difference of these two values that we have, 7 minus 2. And remember, the larger number should always be first. So we shall always be 7 minus 2, and that's 2 minus 7. And we're going to equal this to this further value in our sequence, which in this case is 1.5. Okay, so we're going to start by dividing both sides by 48. So we could start isolating the r. So this reduces and we end up with r to the 7 minus 2 power, which is the 5th power. And 1.5 divided by 48, that equals to the fraction of 1 over 32. As a decimal value, that's approximately 0. What did I have? What did I say? 0.03125. But we're going to leave it as a fraction. Now, in this situation, we're going to get the 5th root of our function. And like I said on the previous example, I'll show you tomorrow in class how to take the 5th root of a value. So we're going to take the 5th root of r to the 5th, and we're going to take the 5th root of 1 over 32. And that's going to give us that r is equal to 1 over 2. Let me just verify. Double check that I got it correct. Yep, 1 over 2. So there we have our common ratio. So now that we have our common ratio, let me draw a vertical line right here. I can now come up with the equation. So all I have to do is just use either of these two values. So I'm going to start again, use the smaller one. I'm going to use this one right here. So g of n is going to equal to the 48. Our r is now the number 1/2. and we're going to raise this to the n minus this value here, so 2. And that's going to be the general form of our geometric sequence. And now using this, I can evaluate this and figure out what the 12th term is. So 11 minus 2, that's 11 minus 2 is 9. So I have to raise 1/2 to the 9th power and then multiply that with 48. Which equals to the decimal, to the fraction of 3/32. So that is your answer. So in these examples, it's a little bit trickier to figure out what the ratio of r is. We have to use division and then some type of root. And setting it up again has its distinct method. You do not want to do it the other way and start with this value. You always want to start again, put your sequence as you saw in order, and start with the further number in the sequence, which obviously should be this value right there, okay? So you want to start with this and start with the 48, multiply it with your r, and you're going to raise that r to the difference of the terms in the sequence. So the 7th and 8th n values. And we're going to set that equal again to this number right there. From there, we're going to divide like you saw. We divide by this quantity to get, again, a fraction. We always want to write this as a fraction, not as a decimal. And then we'll take the root that corresponds to this exponent there. So since it's to the 5th power, we're going to take the 5th root. Like on this one, it was to the 3rd power, so we took the 3rd root to get rid of that 3. And like I mentioned, I'll show you when you come to class tomorrow how to do this in the calculator. Okay then, well that concludes again our notes on this second part of 2.1. If you have any questions, please send me a message or remind. And like always, I appreciate you watching and I hope you have a great day. Goodbye.